All right, we're finally winding down to the end of the chapter. Let's go ahead and finish strong. The statement reads, find the radiation reaction force on a particle moving with arbitrary velocity in a straight line by reconstructing the argument in section 2.3 without assuming that V at the retarded time is 0. B. Show that this result is consistent in the sense of equation 78 with the power radiated by such a particle in equation 75. Okay, before we get started on this, let's redraw out what the method used in that section was. So here we had a point charge that was split up into a dumbbell where we split the charge Q/2 to the top half, Q/2 to the bottom half, and now we're just looking at the charge as a distribution with kind of globs in it. And that's why we call this the dumbbell method. So you see here that our script R comes from the retarded position to the present position, which is by a length L, and the charges are separated by D. That's our setup. So here from equation 62, we know what the charged particle does in a arbitrary motion. So our charge is Q/2 now, and we just tinker everything down from that original form. And now we're going to define what U is, which is C script R hat minus V, where script R is equal to L dx hat plus dy hat. Again, we can see that from the diagram. V is equal to V x hat, A is equal to A8 or A x hat as well. So script R dot U gives us a C script R minus LV, where script R dot A gives us LA. And then, we want only the x component, so noting that ux is equal to ct over script r minus v, so then we can tidy that up as far as what the u is. So we get ct minus v script r over script r, and now we'll just plug everything in. Not always necessarily the easiest or tidiest thing, but you can see line by line the cancellations and simplifications, expand, cancel, refactor, expand, cancel, refactor, that kind of thing. So in our final line, we are left with Q over 8 pi epsilon naught, 1 over C script R minus LV cubed. And then we have a refactored CL minus V script R times C squared minus U squared minus AC D squared. And we note that E2 equals E1x, again, due to the symmetry of the construction. So here F self is equal to Q2, Q/2, E1 plus E2. And so let that be what it is, move itself through. Now you get Q squared over the 8 again, because when you add E1 and E2 together, you get 8 plus 8 with the 2 in the denominator, with the 2 in the numerator, and that cancels with the Q/2. So yeah, that denominator is right. Simplify down. Now what we need to do is address the statement of the retarded time. So x of t minus x at the retarded time is equal to L, which is equal to Vt plus 1/2 AT squared, blah, blah, blah. Keep going through. That's just the expansion. So big T is equal to t minus the retarded time. V, A, and A dot are all evaluated at the retarded time. So C at big T squared is equal to script R squared is equal to L squared plus D squared. So if we push this all through, I'll have more to say about this, but we just have to be not really worried, but careful with this expansion and putting things in terms of the actual quantities we need. So if we do that and we tidy it up to the best of our ability, what we see here is that we only really need the t squareds there, so we factor that out. And now we can put that gamma term in. And what we're about to see is that with these higher order terms, we could expand that t series as a power series in D and resubstitute things in. It's just the order that we need is going to be playing a big role here. So we're just mimicking the form of what we saw in the section. And if this kind of looks spooky or scary, then I advise you to go look at that section. So we're left with one final expression at the bottom, namely 2a d cubed plus 2b d to the fourth plus a squared d to the fourth. Notice how everything is into the fourth power. That's to the expansion level we need. Okay, and then the right-hand side is as such. You can look at the algebra. The next page is full of algebra, so be careful. What we're trying to do is expand or compare the like powers of d. So, for example, if we're looking at d to the third power, the coefficients are such, and then we solve for a. If we're looking at d to the fourth power, we see that we have two coefficients, 2b plus a squared, and that has to equal to the right-hand side as well from the t series. So I'm going to let you look through this. I'm not going to talk through all the steps. You can see how we need to combine, factor, cancel, distribute, the same algebraic tools we have. And eventually we get to a point where we can have a coefficient just in terms of b once we divide over the 2, and that is useful. So what we have is, once we have that, then we can plug a and b into t, and we yield the expression for t. And again, based on what higher order terms that we actually want, we can modify accordingly. So then from there, we can do the same thing for the L, and we have the expansion for L. Mathematica actually has a really cool tool where they can help you with these expansions. So just type in what you want. Again, I'm not going to walk through all the algebra. I think you can just pause the video and see it for yourself. That's a lot of typing. So go ahead and pause it. But for now, I'm moving on. We have more of the same thing because we need to define everything in that electric field, right? So we still have to have the script R. We have to have the C script R minus LV. And then we have to have CL minus V script R, all using these expansions. And of course, we have to have the C script R minus LV to the -3 power, since that was part of the form. So go ahead, take your time, pause the video, look through how we had to address all of these things and refactor. I honestly can't blame you if you don't want to read it all, but that's what we have to do in these approximation schemes. Use all the tools you have or the tables available. And then finally, what we see here is that now we can actually put these together in the F self, and we see that we have a parentheses here just for the constants of gamma and CD to the cubic, and then we also have parentheses for the C R minus LV to the 1 over to the over 3 power. Again, we kind of know how that works. And then the curly brackets come from everything else. And now again, what do you think we're going to have to do but to expand and tidy everything up? This is a never-ending cycle. And good luck. Take your time. Walk through the steps. I'm going to go on to the next page now, but we can see what we need to do now. So switching T with the retarded time. So switching to T, we have the retarded velocity, or the velocity at the retarded time, is equal to Vt plus V dot T with the expansion Tr minus T, so on and so forth. So we have Vt plus At minus big T, and we already know what big T is, so we just let V of T minus gamma D over C, and now we can fiddle away through with how to evaluate things with that retarded, with the velocity at the retarded time. Okay, so we have L, and then we move on to gamma, and take your time with it. Again, not nice, not easy, not clean at all. And now we are left back to evaluating the F self, which again is still in the expansion form, and we just have to plug in what that V of what these factors are. So have fun. We see we have 4 lines to simplify the F self, and then we'll go ahead and notice a couple things in this expansion. The first term is the electromagnetic mass. The radiation reaction itself is the second term, so the gamma to the 4th power. Okay, so that's what we're interested in, is the interaction term of the radiation. and that's where we get to the fourth term for gamma, or the gamma to the fourth power, and the parentheses that follow. So notice that with the Lamar formula, or the F radiation before, we just had A dot. Now in this expansion, we have this fraction with 3 VA squared gamma squared over C squared. And guess what? The more that we're looking at, the worse this thing gets with respect to higher order terms. Similarly, for part B, F radiation, we have what we know what A is. We're just going to keep our lives simple. And P is equal to A, little a squared gamma to the sixth. And we must show that, except for the boundary terms, see section 2.2. So let's go ahead and show it. We take the F radian of radiation, V dt, from T1 to 2, and we show that that's equal to the negative integral of the power. So let the math work its way through, fiddle it down, take your derivative, which we do by d by dt for gamma to the fourth, V, power rule, product rule, of course. Substitute it all in, and then finally, after we tidy up that derivative and the substitutions, what we see is that the integrals start to come together, and hence we have in the second to last line T1 to T2 gamma to the fourth with that parentheses dt, which is what we found, is equal to now integration by parts and the expansions. And then we show finally that F radiation integral goes to gamma to the fourth VA evaluated from T1 to T2 minus the integral T1 to T2 of gamma to the sixth AT squared, or A squared dt, and thus we are done.